In this practice set, we are going to focus on the acid-catalyzed addition of water to alkenes, also called the acid-catalyzed hydration. We will first review why an acid-catalyzed is required. Then we will walk through the reaction mechanism. And finally use the mechanism to predict the major products of several alkene hydration reactions. As you walk through the examples, pay closer attention to where proton adds, where the carbocation forms, and which carbon ultimately receives the hydroxyl group. Acid-catalyzed hydration requires an acid because the alkene must first react with a sufficiently strong electrophile. Water by itself does not provide enough hydrogen ion to protonate the carbon-carbon double bond effectively. So the reaction does not proceed at a usual rate without an acid. In this example shown in here, we have ethylene reacting with water in the presence of phosphoric acid to produce ethanol. The acid generates a strong electrophilic proton that protonates or begins the reaction. The pi electrons of the alkene can then attack that proton, starting the addition process. The important idea here is that acid acts as a catalyst. It participates in the reaction mechanism, but it regenerates before the reaction is complete. Overall, the elements of water, H plus and OH minus, are added across the double bond to form an alcohol. Now let's look at the mechanism. The first step is protonation of an alkene. The pi bond acts as the nucleophile and attacks a proton from hydronium. At the same time, the oxygen-hydrogen bond in hydronium breaks and the electrons return to oxygen. This creates a new carbon-hydrogen bond and produces a carbocation intermediate. The position of the carbocation is really important. Protonation occurs in the direction that gives more stable carbocation. In this example, with the 2-methylpropene, proton adds to the less substituted alkene carbon, leaving the positive charge on the more substituted carbon. This produces a tertiary carbocation, which is more stable than the alternative primary carbocation. This is the origin of Markovnikov orientation observed in the product. In the second step, water acts as the nucleophile. A lone pair on the oxygen attacks the positively charged carbon and forms a carbon-oxygen bond. At this point, the oxygen has 3 bonds and carries a positive charge, giving a protonated alcohol. In the third step, another water molecule comes and acts as a base and removes proton from the oxygen. This gives neutral alcohol and regenerates hydronium. So the acid catalyst is recovered. Because this mechanism contains a carbocation intermediate, carbocation rearrangements are possible. When you solve these reactions, always check whether a hydride shift or an alkyl shift could produce a more stable carbocation before water attacks. Now, apply the mechanism to the 2 reactions shown. Before I work them out, pause the video and try to predict the major product of each reaction. Remember, first determine where protonation gives the more stable carbocation. Then place the hydroxyl group on the carbon that carried the positive charge. First reaction, 1-butene. The double bond is terminal. Protonation can lead either a primary carbocation or a secondary carbocation. Secondary carbocation is more stable, so the hydrogen adds to the terminal carbon and it will produce a carbocation on the second carbon. Water will come and attack this carbocation, and finally we are going to end up having a OH group on the second position. So we are going to produce 2-butanol as the major product in this first reaction. When we look at the next reaction, in the next reaction we have 1-methyl cyclohexene as our starting material. In there, if we take a closer look at the double bond, we have methyl substitution on one of the sp2 carbons. So it is going to be the most substituted carbon. So when we try to predict the product, we draw the rest of the molecule as it is. The H plus or the electrophile is going to add to the sp2 carbon where we have more hydrogens, and that will create the positive charge in here. Since it is producing a tertiary carbocation, no rearrangements are necessary. So water molecule will come and attack this positive charge, giving us our product. So we will see this molecule as our product, and it is going to be 1-methyl cyclohexanol. For acid-catalyzed hydration, use the carbocation mechanism rather than simply memorizing the product. Identify the most stable carbocation, check for possible rearrangements, allow water to attack, and then deprotonate to form the alcohol. That sequence will help you to predict the major product consistently.